In this video I will try to describe how you can calculate reaction forces and bolts that are securing a flange. This is not the first time I'm making this video. I tried an attempt earlier by only using the whiteboard behind, but this time I will try to use some pictures to show it more clearly, the figures and the calculations. I used a lot of time to find the way to do this, and eventually I found a good book that describe this. So I hope this will be accessible for you, so you can use it whatever you're doing. Good luck. Okay, let's get started. I will try to show you how you can calculate the reaction forces and bolts that is securing a flange. Here we're having the flange, that is a steel plate. This is rather thick. This one is connected to a wall with a lot of bolts here. And there's a force that is pulling on this beam here. And that is making like all these bolts are feeling tension due to the force here. And that is what we're going to calculate now. But that is a little difficult, and I will show you why now. First, we'll look on a simpler setup. This is also a flange, but only with 4 bolts and a rod and a force that is pulling on it. This one you also have to pretend that is also mounted onto a wall. But for this first example now, we will only pretend that there is bolts in the 2 upper holes. Check it out. Then you can set up a graphical display like this. Here's the plate, the flange. Here's the beam. Force is pulling there. And when the force is pulling, there is tension in the bolts. That is here described with an arrow, and the reaction force F2. The force is F1. Here are some data, some length and some forces. And in order to calculate the reaction force here, that's straightforward. We set this as the positive direction for the moment, and since this object is stationary, it is not moving or accelerating. We know that the moments are, the sum of moments is 0. So because it is balanced out, it's in equilibrium. What we do then is we set up the forces that pulling it or the moments that is pulling it in the positive direction, and we also know that it is pivoting around this point down here. F1 multiplied L1, that is the force multiplied with the distance, which gives a moment. And as the opposing force is the F2 multiplied with the distance L2. These have to be in equilibrium. Then we know F1, L1, and L2. So we just solve for F2 and find that in this example, F2 is 2273 Newton. Okay, quite straightforward. Now we're going to have a slightly different example. This is this one, where we only are using the bottom line with bolts. Do exactly the same thing, but since the length here now is much shorter than this one, the force F3 as a reaction force is 10,613, and in the last one it was 2,000 something. So we see here that the distance is very or the force is very depending on the distance, naturally. Okay, in the next example, we're going to calculate it when we have bolts in both upper and lower section. Here we have also the same data. So we have still the force F1 that is pulling here, and we get reaction forces in both F1 F2 and F3, and we have the length or the distances. And we try to set up the equation. We have which is pulling us in the positive direction and in the negative direction and in the negative direction. But you see here, when we have put in or inserted all the data we know, we see that there still are two unknowns, and this is the only equation we have, and we don't have any relation between F2 and F3. So there are no way that we can calculate this, and that is the problem. And in this video, we'll try to show you how you can do that. But first, I will also explain a little about a beam and how you can calculate the stress in a beam that is supported here. So this is a beam which is supported on these two triangles, and there's a force in the middle here pushing downwards, and there are reaction forces in both supports. Okay, here we have the force F1 pushing downwards. This one then will flex slightly. On the top you will have compression, and in bottom you will have tension or stretch. This is what says here. In the middle there will not be anything. So this one is giving a little flex down. Here's a cross-section area picture of the beam, height h and width b. The force is located at the length L from one of the supports. Okay, this is a quite classical task, and in order to calculate the tension in let's say down here at the stretch side, sigma, which is the unit for, or the letter for tension, is moment divided by second moment of area multiplied with variable y. The moment here can easily be calculated by taking force F2 and multiplied with a L. And now we are basically, what we want to do at all in this example is to show you the use of second moment of area, which here is denoted by Ix. This will give you the calculation for the tension. And in the next slide, see here, we show that Ix is actually calculated with a very small area around here, and the distance from the center line and up, or to the pivot line, or to the neutral axis, and up to that area squared. That is how we calculate this. Normally, when you would do this like in a textbook task, you will find some tables that does this for you or show you how it is. And for a square beam like this, or not square but rectangular, it is BH in power of 3 divided by 12. That is useful. If you are to calculate this for like any shape, there's some sort of double integral, and you will find much more of that if you search for second moment of area. But that is not what we're going into now. We're going back to our example here, and we see here this figure here. So when I have an F that is pushing downwards here, in the upper part you will get compression, in the bottom part you will get tension, and it is largest at the outermost fiber on both ends, and it declines until it gets 0, and then it sort of changes the sign and gets in a negative way. That is important to remember. Okay, so we'll now try to calculate the force. Sorry, I mean the stress in the outermost fiber down here by using the calculations here. So the formula, it's not here anywhere, but yeah, it is here actually. So first we'll calculate the moment. We use a static analysis and find F2 and F3. F2 is here calculated to be 15,000 Newton, and the length L is 1,000 millimeter. That will give a moment of 15 multiplied 10 in the power of 6 Newton millimeter. Okay, that is the unit. And then we will, in this example, we will just use the table way of calculating the second moment of area, which is B multiplied H by the power of 3 divided by 12. Here we have inserted all the values, and we calculate the second moment of area of this beam. So in order to do this, we are always interested in the stretch, or I mean in the stress in the outermost fiber, because that's where it is. And if a crack starts, it always starts there. And if there first is a crack, it will open for more and more propagation of the crack. So this is what you're trying to avoid in a mechanical design. Well, what you do, you calculate the moment divided by the second moment of area, and you multiply it with the distance from the neutral axis and up to the outermost fiber. Here, this is 175 millimeter, because the height of the whole beam was 350 millimeter. This gives a stress at 4.9 Newton per millimeter squared at the bottom here, which is tension, or in the top here, which is compression. It's the same. We will also use the same to calculate the stress at the center point, or center axis, along the center axis. We do the same exact. The only change here now is that y is 0. Yeah, that's a very important thing I probably forgot to remember. Y here is the distance from the central or the neutral axis and up to the small area where you want to calculate the stress. So now we set this as 0, so it's basically at the neutral line. And what you find then is that the stress is 0. In the next example, we are just going to do the same again and calculate the stress like halfway between 0 and the outermost fiber, which is at point y 87.5. We do the same, and we also see that the stress here is 2.45 Newton per millimeter. Okay. This is not anything new, but it just gives you a connection with the concept of the second moment of area and moment here, and that can be used to calculate the stress. The stress in an infinitely small area somewhere along your beam. Okay, and then we're going back to our previous example. This is a familiar flange with a beam and a force pulling on it. Okay, for this method, we are going to use bolts. In this example, I put in 4 M24 bolts in the holes, and the stress area for the bolts, you can find it in tables, is 353 millimeters squared. And we're going to calculate the second moment of area of like this of this cross section, which is like 0.01 millimeter behind this flange, where is only the bolts are coming through. So we basically have 4 areas we want to include in this calculation, and that is the 4 square, or the 4 stress areas of the bolts, like here. So again, we have now this flange. It is pulled with a force here. We know the L1 out to the force, and that is making us able to calculate the moment. We will set the pivot axis at the corner down there, and that is the blue line is marking here. I call it XX, and I will now calculate the second moment of area for the cross section that is just behind the flange. And a few simplifications I've done here. I'm doing here. That is, I will calculate that with the bolts, but I will put the whole area of the bolt in one single point. That is not entirely correct, but it will be a very good estimation, and I don't think you will get very big deviation in result by doing this way. Another simplification is that I put the pivot axis down here at the blue line. It might, I mean, if this flange is perfectly stiff and there is no bending in it at all, this will be correct. But in most cases, there will be a slight bending, and this pivot axis is perhaps a little upward. But again, I think it's a quite good estimation. So what I'll do now is to calculate the second moment of area, which is done by this. So I take the area of the bolt and multiply it with the distance from the pivot axis squared. And I can sum 1, 2, 3, 4 of them. So here I've just said what it is. A is the bolt stress area, and Y is the shortest distance to the pivot axis. This is similar to this one. As in the beam, the pivot axis was at the center. Here it will be at the bottom, because this is what it will be tilting over. Y is the distance to the area, and area is, in this calculation, it was like an infinite small area. But here it has a certain area. Okay. To calculate the stress in the area up here, I come up with this formula again. It says sigma equals moment divided by second moment of area multiplied y. First, I calculate the moment, F1 multiply L1, and get this moment. Secondly, this is what's important now, is to calculate the second moment of area for this particular bolt image. So I will take the area here, multiply it with the distance squared, and since there are 2 bolts at the same distance, I will multiply it with 2 again. And then I will plus it with another area of the same size, and multiply that with y2 squared, and there are also 2 bolts up here. That gives me another multiplication with 2. So that's what I've done here. The area, I'm just taking it out of the brackets, but 2 multiplied with y1 squared and 2 multiplied with y2 squared. Inserting the numbers and getting a second moment of area. And this is, now you see that this is the same example as we were unable to solve with classical static analysis. So what this will show us now is it will calculate the stress in the bolt, but not the force, but just the stress in the bolt. As you see, again, the y here is the distance from the pivot axis and up to the position of the stressed area, and that is also, like here, it will propagate and grow as you have a longer length y. By doing this, I am able to calculate the stress, which follows this formula. And then I will insert y for the distance from the pivot axis and up to the lower 2 bolts. That is 106 millimeter, which will give me a stress of 0.68 Newton per millimeter squared. And for the upper 2 bolts, it will be 3.13 Newton per millimeter squared. Remember, this is stress, this is not force. Okay, so I'll also go out to another part of this, is that if we have just like anything that is pulled or pushed together, to calculate the stress in that one, you will take the area that the forces are distributed over, and you will take the force and divide it by the area the force is equally distributed over. That gives you our formula here. Stress equals a force divided by area. I can also rearrange this a little and say that force is also equal to stress multiplied with the area. And the area for this bolt, I know it's 353 millimeters squared. And I know also the stress in the bolt. For the 2 lower one, it is 0.68 Newton per millimeter. For the top one, it's 3.13 Newton per millimeter. And that makes me able to calculate the force in the bolt. So I simply take the stress multiplied with the area and get out the force in the bolt. And this is, of course, the reaction force to the force that was pulling out here on the beam. So basically what we have been doing now is that we have found a connection or a relation between like bending moment and a normal stress. And we're using that to calculate the reaction forces. And that is rather neat, and that's rather neat. I mean, and I really like that, and that is why I wanted to show this. Okay, so getting a little further. This is the original image that we showed. This is a larger flange with a lot of bolts. The same principle. And here it shows I have here made a drawing and showed all distances from the pivot line, which is down here. And I also show like a photo from an Excel sheet I have made, which basically calculates this. I put in all the distances from the pivot line. I set in how many bolts are on each line. Based on that, I can calculate the second moment of area. I have to set in the force and the distance to the force, which together makes a moment. And based on that, here is the area of the bolt. That one is not actually necessary. I mean, it will actually be sort of diminished, but I really like to make some like small calculations underneath and find like one step at a time. So that's why I really like to use to add the area in there. But I mean, yeah, it doesn't really matter. Yeah, I'll just set up here like a little description of what it is. AB here, yeah, down here you can see it very easily. The reaction forces here are calculated this way. Force is moment divided by second moment of area, multiplied with the distance again up here, and multiplied with the area or the stress area. And that is giving me the reaction forces here due to this force. Another nice thing here is that we can also do the same thing if you have like this force is they are not following in straight line, or it was maybe a force that is going in this direction, and you decompose it into a force in x direction and a force in the y direction. And first you have to calculate the reaction forces in a bolt based on the force in x direction that is tilting this flange over this pivot line, and you are using these values to calculate the reaction forces. Secondly, you're doing the same with the Fy force, which is tilting or trying to tilt the flange over this pivot line, and you're using then these distances to calculate the reaction forces. And here you can calculate, you have the list of forces in each direction, and you can just sum them. These two images are not connected here. There was for an example with 60 volts, but the principle is still the same. You can even if you have a force that is pulling towards you, you can also calculate that as a normal force if it is evenly distributed, and also add it to the calculation. Remember, what we have calculated now is only reaction forces. If any of these bolts are pre-tensioned, as they might be, that will of course come in addition. Yeah, one last thing I wanted to show you is that in this example, let's say that you had a force that is pulling towards you. The distances out to all these bolts are the same, and this is a fairly stiff flange. So here it's correct to assume that that the force is distributed or quite evenly on all the bolts. But you will find examples where it isn't. Might even be a little surprising. This is a simulation that was performed. This is a flange with two ears, and there's a bolt going here and it's pulling it upwards. And we added a lot of hole around here, and we tried to calculate. I mean, if we assume that the normal force here would be evenly distributed, it would be like a fifth of the force on each hole. But what we saw, this is done in a SolidWorks simulation using FAA method. But we saw here that the hole or the bolt in 1 and 5 took a very large amount of the force, because they are closest to the force, of course, but again, or as a reaction force, I mean. And these two holes or bolts were basically didn't do anything, and this did maybe a little less of a third of this one. So be careful, and remember that it is not always correct to just evenly distribute reaction forces around. Yeah, so that is what I wanted to show you, and I hope it was for benefit for you. And if there's a question, please add it in a comment. Okay, goodbye.